Hello and welcome students. In this video, we are going to talk about potential, kinetic, free and activation energy. For the very basic and the beginning of the concept, we will talk about energy. So energy, as you can see here in the T chart, is explained into two types, potential and kinetic. So potential energy, basically, it comes from the word having a potential to do work. So potential energy is basically the energy of things that are not in motion or that are not using that energy as of now. So it is also defined as the energy that bonds, that hold molecules together. That energy that they have is given as potential energy. They have the potential to change it into, other forms of energy. Now, the other type of energy, when we talk about potential, is kinetic energy. And kinetic energy is basically the energy of a moving object. And that reminds me that there is a motorcycle brand also in India which is named as Kinetic. So basically, the meaning will be kinetic is something, the energy of a moving object. So when you're using that energy that was stored as a potential, you're now going ahead and using it. So all right, on the next page, we are going to take a look at little bit more details of this concept. Now we will take a look at another type of energy of the system, and the name is entropy. Entropy is basically the measure of how energy is distributed in the system. It is denoted by delta S, and basically in layman terms, it will mean that it is the disorder in a system. For example, in gases, the disorder is higher, as compared to solids because um, they are the atoms are more free to move, so there is more disorder. So gases will have higher entropy as compared to solids. The unit for entropy is joules per Kelvin as temperature. And we will move on to the another type of energy, which is little different than entropy, and it is called enthalpy. All right, so basically it is the energy of the system. So it could basically mean, there is disorder in the system. There is some energy that is being used from outside, from the environment. There's some energy lost in the system. So enthalpy would be the sum total of the total energy of the system. And enthalpy is denoted by delta H. All right. Now on the next page, we will take a look at more notes about these quantities and how they are related to Gibbs free energy. All right, so on this page, we will talk about Gibbs free energy. And the very first point, we will give some respect to Mr. Josiah Gibbs. He was actually the founder of Gibbs free energy. And it is denoted by the letter G. And basically, it actually gives you an equation for the total energy, free energy available in the system. So now in thermodynamics, there's a very important equation that is being used in order to calculate the Gibbs free energy of a system. And that is given by delta G. That means change in Gibbs free energy equals delta H, which is enthalpy, minus T is for temperature times delta S. Now let us label our formulas. Delta G is Gibbs free energy. So he came up with this formula or to calculate the free energy available in the system if we already know the enthalpy and the entropy of the system. and when the temperature is given to us. Temperature is in Kelvin, and delta S is change in entropy. That means the disorder of the system, and is given by kilojoules per mole. All right. So this is, really important about Gibbs free energy, just an introduction. And then on the next page, we will take a look at um, how Gibbs free energy helps us study the system a little bit more. All right. All right, so on this page, students, we are going to talk about Gibbs free energy and how the value of delta G when we solve the equation is going to tell us whether the reaction will be spontaneous, non-spontaneous, or is at equilibrium. So there will be no change when it's at equilibrium. So basically, whenever your delta G value, when we solve the questions, whenever that value is less than 0, the reaction is going to be spontaneous. It's going to happen automatically. When delta G is 0, it is at equilibrium. There will be no change. And then when its delta G is greater than 0, it is non-spontaneous. So some energy is going to be actually applied to the system to have, the reaction being completed. So let us take a look at, what it basically means in a graphical approach if we take a look at it in layman terms. So for example, if there is a little ball here, and I mean, if the ball is right here, the falling down of the ball is a spontaneous reaction. So it's going to automatically happen and it's going to easily go through this. But if the ball is right here, we need some energy to make the ball go uphill. I mean, that's just one way to look at it, although it's not a very perfect example. But I mean, you get the point that between spontaneous and non-spontaneous. So, all right, on the next page, we'll take a look at some examples. All right, so on this page, we are going to take a look at a question that I got from your book. Basically, they are giving you the value of delta H is negative 100 kilojoules per mole. Delta S is 200 joules per mole Kelvin. Temperature is 300. And they are asking you the value of delta G, the free energy available in the system. So what we basically need to do is just some basic math here. What we'll do is we have our formula that we had on last page. Delta G equals delta H minus temperature times delta S, which is our entropy is delta S. So now we are just going to plug in the values here and we'll see what our answer will be. So delta H is negative 100 minus 300 was the temperature. So I have my temperature here times delta S. Delta S is 200 joules per mole. All right, so it is negative 100 minus 300. Okay, now as I'm doing this question, students, I'm thinking that my delta H is in kilojoules per mole and my delta S is in joules per mole. So that's a problem here. We cannot solve until the units are same. So what I'm going to do is I'm going to convert the kilojoules to, so I'm going to convert the joules to kilojoules, which is 200 divided by 1000. So that is going to be kilojoules per mole now this time. All right, so that gives me negative 100 minus 300 times. The zeros are gone here. So it is 0.2, and which is negative 100 minus 3 times 2 is 6. But because there's a decimal, so my answer will be 60. And it is negative 160 kilojoules per mole. So delta G value here is That means that is the free Gibbs energy that is available in the system is negative 160 kilojoules per mole. So that means because the value of Gibbs free energy is negative, this reaction is going to be a spontaneous reaction. All right, let us take a look at another question on the next page. All right, so for this question, students, we are given delta H value is 300 kilojoules per mole, and delta S value is 150 joules per mole. We are now required to calculate the temperature. Another detail that was given in the question is that there is a reversible equilibrium established of the given, material or system that we are studying here. So reversible equilibrium could be that we have, let us say any system, and it has some, there are two ways in which we can have the material there. So in the system, we have the same compound, which is, available in liquid form and in gaseous form. And what is happening is there is a reversible equilibrium. So we are having it in both states, liquid as well as gaseous. And so it is happening, on both the ways. Basically, example could be water. We are boiling the water, we are having it in gaseous form. Gases go up, they condense, and they're coming back as water again back to us. So whenever there is reversible equilibrium established, our delta G is actually equal to 0. So the value of delta G is going to be 0 here, and we are going to actually establish our equation, which will be delta H minus T delta S. Now remember, here we are going to calculate T. So for calculation of T, I'm going to add T delta S on both the sides, so that it goes away from here, and I now have T delta S equals delta H. Now, because I'm going to calculate T, I have to have T isolated. So what I'll do is I'll divide by delta S on both the sides. And now after dividing delta S on both the sides, I actually get a formula for value of the temperature, which is delta H divided by delta S. That means enthalpy of the system divided by entropy of the system actually gives me the value of temperature of the system. How cool is that? So now let us plug in the values. So we'll have 300 kilojoules per mole divided by 150 joules per mole. Now we just came to my mind that as I was writing them, kilojoules over joules, there's a problem here. I have kilojoules here and joules here. They need to be the same unit for me to be able to actually divide them. So we can just convert this kilojoules to joules. And remember, 1 kilojoule equals 1000 joules. So I'm going to apply that here. So I'm going to multiply this 300 basically by 1000 in order to convert it to joules. And I have 150 here. All right, let's see how many zeros we have. 1, 2, 3, 4, 5. Divided by 150. Now I can get rid of the zeros. And 15 times what is 30? 15 times 2 is 30. So I'll have 2 and then I'll have 3 zeros next to it. So I can say that the temperature of the system is going to be 2000 Kelvin. So they can give you questions where, they'll actually hide the information that, the delta G is actually 0, and you'll have to, read the question or see and pick up words where they use the words like reversible equilibrium is established. So they can even ask you values to calculate. So, from here onwards, basically, it's after plugging in the values is your basic math that we applied. All right. So on the next page, we'll take a look at a little bit of more questions. All right, so another type of questions that you could be asked are going to be related to entropy. Entropy, remember, was delta S, and it is basically actually the measurement of disorder in a system. So disorder basically will be, gases will have more disorder because there's more available space for atoms to move around, So they are more disorderly as compared to solids. So solids have a very low entropy as compared to gases. So the first question that we are going to look at is this one. Here we have carbon plus oxygen give us carbon dioxide. So what are we having? We are having solid form of carbon plus gaseous form. So we have solid and a gas is giving us the end result is gas. So here we had low amount of gases. We just had one gas. And then our end product was all gases. So I would say that the entropy here is going to be higher for the products as the product is a gas. And if you can remember, gases are more disordered. All right, let's take a look at the next question, which is water in the form of gas. We are condensing it to get water in the form of liquid. Pretty clear from here, just if you look at the equation, you can see that we are going from a very disorderly state where our entropy is higher to we are going to where our entropy is lower because liquids will have lower. So here we can say that the delta S is negative because the entropy of the system is decreasing. So it basically, helps you to figure out as to from what state you're moving on to what state. Are you moving from disorder to order or order to disorder? So you just have to study the equation carefully. All right, let's move on to the next example. All right, on this question, we have sulfur dioxide in gaseous form plus oxygen, which is also gas, to give us sulfur trioxide, one gas. So basically, if we take a look at the system, we have one gas plus one gas to give us one gas. So two gases were here, so our entropy is higher on this side, whereas over here we had just one gas as an end product. So we will say that our delta S will be negative as the entropy of the system is decreasing. All right, next question. We have question number 4, magnesium oxide, which is in solid form, combines with carbon dioxide, which is in gaseous form, to give us magnesium carbonate. So that is also given to us that it's in solid form. So basically, you can see that we had a gaseous form here, but we are ending up with solid form. So we had high entropy on the left side, whereas we are having very low entropy on the right-hand side. So we can say that we are moving from high S to a low S, hence S is decreasing. All right. On the next page, let's continue a couple more. All right, so on this question, they are asking us, we have two samples of carbon dioxide in gaseous form. The temperature on the left-hand side sample is 300 Kelvin. The temperature on the right-hand side is 400 Kelvin. Now we are in a dilemma, what to do? Because they both are in gaseous form, how do we figure out the entropy? Now always remember whenever the temperature is also provided to you. Any sample with higher temperature will always have higher entropy. So that is something to remember. So high temperature will also give you high entropy. Now why that? Because at higher temperature, the gas molecules will move faster. So you can just take a note of that, that higher the temperature, it will give rise to higher entropy because gas molecules will move faster at a higher temperature. All right, so we'll resume our video. We'll complete our video, sorry, at this question. It's a pretty long video, so we will take a look at potential energy diagrams in our next video. Thank you so much for joining, and I'll see you in my next one. Have a good one. Bye.